In this video, we're going to be talking about static electricity, structure of an atom, and a bunch of common examples of where charging, attraction, and repulsion occur. Now, the first thing we want to hit is the structure of an atom. So we would just want to know that on the outer parts of the atom, we have the negatively charged electrons, and in the center, we have the protons and the neutrons. But since the neutrons aren't electrically charged, we just care about the positively charged protons in the nucleus. With that being said, the importance of that is knowing that the electrons are the only particle transferred. So since the protons can't be pulled from the nucleus, the electrons are going to be the ones that move from place to place. Now, if we take a look at a couple of common cases, we're going to take a look at two people over here and say, for example, we have a person rubbing their feet on the ground. Now we have a softer carpeted material where the electrons are not super strongly attracted to the nucleus. And then we have some rubber-soled shoes where they're a little bit more insulated. So they're going to be able to pull the electrons from the carpet up into the shoes. Now, because electrons repel one another, as you start collecting electrons, they're going to naturally repel each other and spread themselves out across your body. Now, when you're electrically charged, because there's an imbalance of positives and negatives, and now you're mostly negatively charged, a couple things may happen. Number one, your hair might start to stick up a little bit because those electrons are repelling one another. And since your hair has a very low mass, they are able to repel one another and then sort of have this staticky look where they're pushing away from your head. Now, if you're very negatively charged, things just naturally want to become neutral. So if you touch something that's conductive enough, it's going to give you a static shock. Now, the static shock you feel is those little electrons jumping out of your finger to help neutralize your body. In a second case, you can also be positively charged as well. Now, how are you positively charged? From things like going down a slide or sliding down a plastic bench where you're in contact with something that is very insulated and it pulls the electrons from you. In that case, if you touch something that's fairly conductive, the electrons jump into your finger and you still have that same sensation of that static shock. Now, let's look at the classic case of rubbing a balloon onto a sweater, where again the balloon is more insulated. Its attraction between its nucleus and its electrons is going to be greater than that of the shirt. So once you put these two into contact with each other, they first are fairly neutral, which means that they have a pretty even mix of protons and electrons. Now the charging happens once there's an imbalance of charge. So because of the conservation of charge, whatever negative charges the balloon gains, the shirt loses. So say, for example, if this develops a charge of, we'll say, -2, then this would be a charge of +2, because the amount of electrons gained by the balloon is the exact amount lost by the shirt. So in the end, with cases of friction and pulling electrons from one place to another, you always have two things that are equally charged but opposite signs, one positive, one negative, because the electrons go from here to here. Now, if we take that negatively charged balloon and it has quite a bit of electrons on it, those electrons are mostly going to stay on one side of the balloon. They will not spread out very much because the balloon is very good at holding them in place. You can put it close to just about anything and it's going to stick to it, which is a force of attraction. So if you bring it next to a wall, it's going to do something where it gets attracted to the protons in the wall and it repels the electrons. Now, the protons really aren't being released from the nucleus, but they feel the attraction from the electrons in the balloon. So they're going to get pulled in towards the balloon and vice versa, and the electrons are going to kind of get scooted back some. Those ones can actually move from the atom a bit, usually the ones that are in close proximity to the balloon. Now, this is a process called polarization. where the charges begin to separate, and then there's a force of attraction. So um, it mostly looks like the balloon is just getting attracted to the wall, but it's also the wall getting attracted to the balloon, because every force has an equal and opposite force. But when you take a look at the thing that has a lower mass, that's the one that always seems like it's getting the greatest amount of force. Just like between the sun and the earth, they have an equal and opposite force of gravity between them, but because the sun's very large mass, you're not going to see quite as much movement acceleration from it. Now, let's take a look at two more cases to wrap up these ideas about charging. Let's say, for example, we had this plastic rod that was rubbed against maybe something soft like this sweater, and it collected a bunch of negative charges. So it's got some positive on there, but it's got some more negative, and then same thing with this one over here. Okay, what it's going to do is if you have something like a neutral can, like an aluminum or tin can, it's a conductive material, which means the charges are going to move a little bit more easily than the average material, such as water or paper or wood. So once this negatively charged particle or rod comes close to it, it's going to have the positives on this side and the negatives on that side. And then again, there's going to be some attraction there. Okay, again, it's an equal and opposite force, so the rod actually gets attracted too, but this is probably held on to by a person, so it's not necessarily going to fling out of the person's hand and then touch the can, but the can is going to pull to the right, and it's actually going to start rolling. And if you wanted to, in addition, if you touch this end, because the left side of the can is predominantly negatively charged, you could get a little shock from there and pull some of the electrons out of the can and make it even more positive looking to the rod. Now, in this case over here, there's also going to be some attraction too. There's going to be the positives that are pulling in towards these negatives and the negatives that are getting repelled. But the effect for the can is much more than the water, because the can is a conductor, so the charges are going to move more easily. And if they move more, then the separation of charges is going to cause more of a positive look to the right side of the can and more of a negative look to the left side. And then in turn causing more attraction between these two objects right here. Now, you can attract a bubble or a stream of water from a faucet, which is actually a fairly common demonstration. And then you could have a bubble slide across a surface, or you could have a thin stream of water get bent towards a negatively charged or positively charged object as well. Okay, so if these were positively charged, these green charges would just get flipped because the electrons would try to scoot closer. So when taking a look at all these interactions, with the static shock would be electrons jumping in or out of an object to help neutralize it. And then with cases of friction, remember the charge is conserved, so they're going to have equal charges and opposite signs. And then in a lot of cases, there's some sort of stickiness or attraction. That's because a lot of things get polarized, and then there's a force of attraction there. So I hope that was helpful in helping you understand a bunch of static electricity examples where they attract and repel. Thank you for watching and listening.